What the heck? And you may recognize what this is. This is the nth Fibonacci number, right? And Fibonacci numbers start off with f0 being 0 and f1 being 1, and you simply add the previous two terms to get the next one. So f2 is 1 because 0 plus 1 is 1, f3 is 1 plus 1, which is 2, f4, which is 1 plus 2, which is 3, and f5 is 2 plus 3, which is 5, and in fact this is the only Fibonacci number which is equal to its index. So I'll just stop there for the sake of it. And so this is going to be our sequence of coefficients, and we're going to find out which function has a Taylor series with these as its coefficients. And the reason this is really easy to do is because we have a very, very nice recursive definition for what the nth Fibonacci number is. It's simply the sum of the previous two. So this actually won't be very difficult at all. So all we have to do is define capital F of x, which is the function we're going to be looking for, which has the Taylor series with coefficients as Fibonacci numbers, and we're going to define it as the sum from n equals 0 to infinity of f sub n of x to the n. And again, we know that this starts 0 times x to the 0, plus 1 times x to the 1, plus 1 times x squared, plus 2 times x cubed. We could theoretically start it at n equals 1, and it would be fine because the first Fibonacci number is 0, and so that term goes away. So we've got this function defined as the series from n equals 1, since the first term is 0 of the Fibonacci sequence, to infinity of f sub n times x to the n. And so we're going to try and figure out what function this is equal to, right? Express it as a function of x. The reason this is an interesting problem to solve is because we can utilize the recursive definition of the Fibonacci sequence to solve this equation. So we know that f of x, or capital F of x, is therefore equal to the sum from n equals 1 to infinity of f sub n minus 1 plus f sub n minus 2. By definition, right? That's the definition of the Fibonacci sequence. This sum of the two previous terms gives you the next term. That's what it is, times x to the n. We can distribute x to the n in, and we get the sum from n equals 1 to infinity of f sub n minus 1 times x to the n plus the sum from n equals 1 to infinity of f sub n minus 2 times x to the n, right? Okay, so what can we do now? Well, we can factor out x from here and sort of make these two things the same, right? That's what we'll do. We can factor out x from here. So we're going to write this as x times the sum from n equals 1 to infinity of f sub n minus 1 times x to the n minus 1. And so this is good. And we're going to factor out x squared from this. N equals 1 to infinity of f sub n minus 2 times x to the n minus 2. So the indices are the same now, or the powers, the n's that appear are the same number. What we're going to do is we're going to add 1 to both of these ends, which means the index has to go down by 1. And so we start at 0, and we get f sub n times x to the n. But this is, again, just the original thing, right? This is x times f of x, capital F of x, except we don't have to start at the 0 term because the first Fibonacci number is 0. So we can actually start at n equals 1 anyway, right? That's the nice thing about the first term being 0. We can just eliminate it. And now what we got to do is we actually have to ask ourselves, what is the negative first Fibonacci term, right? We defined f sub 0 to be 0 and f sub 1 to be 1. Well, we know that the previous two terms have to add up to give the next term. So f sub negative 1 should be whatever I need to add to 0 to get 1. And that number is 1, which means the negative first Fibonacci number is 1. Okay? So let's go with that. So what we're going to do is we're going to take out this first term here. So we're going to rewrite, this is actually just x times capital F of x, so that's good. We have recovered f of x, again, out of this manipulation that we're doing. And this one is x squared times, what is the first thing? So we're plugging in 1 here. We get that the negative first Fibonacci term, since we're plugging in n equals 1 and 1 minus 2 is negative 1, we're going to get 1. and x to the negative 1 is 1 over x. So the first term of this is 1 over x, right? And then the rest of it, starting at n equals 2, we can write like this. Sorry, n minus 2, x to the n minus 2. Okay, so this is the first term of this sequence, and this is the rest of that sequence. And all we're going to do is add 2 to both of these things to then make this index 0, right? So this is going to go to 0, this is going to become 0, and this is going to go to n and n, right? Since we're adding 2 to both of the n's, this one has to go down by 2 so that the series is still the same. And we've again recovered capital F of x, right? Because f of x is defined to be the sum of all the powers of x with coefficients being Fibonacci numbers. So we can use that to our advantage, right? So now we can rewrite this as capital F of x. So we now have a closed form expression, right? We know that capital F of x is equal to x times f of x plus x squared times the quantity 1 over x plus f of x. And now we can just solve for f of x, right? Distribute things in, combine them all together, you know, and solve for capital F of x, and we'll have our answer, right? So what I'm going to do is I'm going to move all the f of x terms to one side, and we're going to solve for it. So we have f of x minus x times f of x, since I'm moving it to that side of the equation, minus x squared times f of x, right? So we have to subtract that over to the other side. So minus x squared times capital F of x, and this is all equal to x, right? Because x squared times 1 over x is x. So this is all equal to x, right? And now all we have to do is factor out our term, capital F of x, right? And we get that capital F of x times 1 minus x squared is equal to x, which means that all we have to do is divide by this quantity, and we find out that capital F of x, the function whose Taylor series has Fibonacci numbers as coefficients, is exactly equal to x divided by 1 minus x squared. Isn't that lovely? So the function whose Taylor series has coefficients that are Fibonacci numbers is x divided by 1 minus x squared. A lovely little fact. Okay, so I hope that's very nice. I hope we enjoyed that. We're going to do one more now. Keeping in line with naming things based on what they are, we're going to let capital H sub n be the nth harmonic number, which according to the videos that I've done on harmonic series and all that, this is going to be equal to the sum from k equals 1 to n of 1 over k. So the sum of the first n reciprocals of integers, which of course diverges as it gets larger and larger. But this is, you know, an interesting thing because we could write it in terms of previous things, and so it'll be very nice to solve. So what we're going to do is, of course, define capital H of x to be equal to these being the coefficients of x to the power of n. So we're going to start at n equals 1 to infinity, and we're going to have h sub n times x to the n. What can we do here? What I'm going to do is I'm going to subtract 1 from the n, or I'm sorry, I'm going to add 1 to the n so that this one has to go down by 1. So this is going to be equal to the sum from n equals 0 to infinity of h sub n plus 1, the n plus first harmonic number, times x to the n plus 1. But what is the n plus first harmonic number? Well, it's the previous harmonic number plus 1 over n plus 1, right? This is equal, this thing right here. So imagine we had the n plus first, or even just taking a look at this. This is equal to the sum from k equals 1 to n minus 1 of 1 over k plus 1 over n, right? To get from the n minus first harmonic number, we have to add the next reciprocal number, which is 1 over n. So to get the n plus first harmonic number, we have to get the nth harmonic number plus 1 over n plus 1. So I'm going to rewrite this as the sum from n equals 0 to infinity of, and I'm replacing h sub n plus 1 with h sub n plus 1 over n plus 1. Right? Because that's literally the definition of what the n plus first harmonic number is. It's the previous one plus 1 over n plus 1. And this is times x to the n plus 1. And all I'm going to do now is distribute this thing into all of these. And we're going to get the sum from n equals 0 to infinity of the nth harmonic number times x to the n minus 1, n plus 1, plus the sum from n equals 0 to infinity of x to the n plus 1 over n plus 1. And that's just distributing the powers of x plus 1, of n plus 1 onto these two terms, right? And now we can do some nice simplifications. We can bring one power of x to the outside, which is great because That's really nice. What we can actually do, very simply, is we can eliminate the first term of this because the first harmonic number is 0, right? If you're not adding anything together, it's an empty sum, and so you start with 0. So we can actually start this at n equals 1. And we can do the same for this in a sense because we can rewrite this by subtracting 1 from both of the n's in the term. We can increase the index by 1 and we'll still have the same equation. So we can do x to the n over n and start at 1. So what we're going to do is we're going to rewrite this one. Because this is a power of x, 1 greater than usual, we can rewrite it with the x on the outside. So I'm going to take that power of x away and I'm going to put it on the outside, right? Because x doesn't depend on n, so we can remove it from the sum. But now we have h of x, the generating function for the harmonic series, in terms of two things we already know. This is x times h of x, and this is negative natural logarithm of 1 minus x, right? This is what we derived earlier in the series. So we know now that h of x is equal to x times h of x plus, or minus in this case, minus the natural logarithm of 1 minus x, because this is equal to negative ln of 1 minus x. And now, of course, we can just solve for h of x. It's really not that hard. All we have to do is subtract it to the other side of the equation and set it equal to negative ln of 1 minus x, factor out h of x, so we'll get h of x times 1 minus x, right, very simply, because it's a factor of those two things. So h of x times 1 minus x, and now we simply divide that down to the other side, and we will have our function. So the generating function for the harmonic series, the function whose Taylor series has the harmonic numbers as coefficients, is equal to negative natural logarithm of 1 minus x divided by 1 minus x. A very, very lovely function. Very nice. And just as a simple little manipulation, we can kind of make this cool looking. We can bring the negative 1 in as a power and do ln of 1 over 1 minus x, and then bring this term out as a factor. So we'll get 1 over 1 minus x, which is this denominator here, times the natural logarithm of 1 over 1 minus x, right? Because the negative 1 goes in as a power and makes it the reciprocal. So this is also an equally valid expression of that function, and it's a very, very beautiful result. So this is the sort of the culmination of what I wanted to do in this video. In future, I may do other generating functions as well, but I just wanted to show these few examples off because they're very, very interesting to try and solve. So thank you very much for watching, and I'll see you in the next video where we're going to explore an infinite sum representation of the harmonic numbers. Not a generating function, but an infinite sum that is equal to the nth harmonic number, and an integral representation or two of the harmonic numbers as well. So thank you very much for watching. Quick little thing, this channel has an Instagram, so it is at what the hectagon, of course, and it has a Twitter also. So this is Instagram, and of course this is Twitter, and it is of course naturally, also what the hectagon, at what the hectagon. Nope, at the hectagon. Whoop, can't spell today. Okay, hectagon. And my email is the incorrectly spelled what the hectagon. Why spell check before you make the email, right? That you can't then change, at gmail.com. Now all of these are in the description if you don't want to have to somehow watch the video and pause it and actually write it down, along with other Instagram, Twitter, YouTube accounts that me and my friend Bill run. He does one for D&D. We together stream on Mixer under the moniker of Fredwood Live. So check the description for other stuff. This is just for my channel. This is my Instagram, at what the hectagon, Twitter, at what the hectagon, and email, at what the hectagon, because I spelled it wrong when I made the email and now I can't change it. So that's the stuff. Thank you for watching, and bye-bye.